Guys, Babirani, SG Mithran, please uh, try to respond if I'm asking something, because otherwise, what's the point of a live session? I could have just recorded and put it up, right? So just try to respond when I'm saying something. So am I audible firstly? And is my screen visible to everyone? Yes? Okay. All right. So we'll be covering tutorial 3 today. And if you are firstly, let's start with if you have any doubts in week 3 lectures. Week 4, I'll be covering in some like maybe a few days later, Thursday or Friday, I'll take an extra session and I'll cover week 4. But today I'm going to cover week 3. So, firstly, I would like to ask whether there are any doubts in the lectures of week 3. Anyone who has any specific doubt, are the calculations okay with everyone, or is anyone getting stuck somewhere? Okay, so since there is no response, I'm assuming that everyone's clear with everything, I suppose. So, all right, let's um, start with the first problem of tutorial 3. Mm, so, the first problem is what is the Legendre transform of the Lagrangian of a classical mechanical system? So let's get like we all know the basic concept of Legendre transform, that basically what Sir told in lectures is that suppose I have a function which is dependent on some variable x, right? This is my function f of x. So I can make a plot of this function x versus f, right? Now Legendre transform of this function with respect to this variable x would mean what? Would simply mean a different kind of representation. Here the representation of each point is simply x comma f of x, right? So this is my abscissa, this is my ordinate, this is my x coordinate, this is my y coordinate. Abscissa ordinate is basically x coordinate and y coordinate. So x is my x coordinate, f of x is my y coordinate. Now we are changing this nomenclature by denoting each point as the one lying on this particular line. So now what I'll be doing is representing this curve by a set of tangents at each point. So if I am giving you a set of tangents which touch each and every point of this, as in at least one point of this curve, then you can use those tangents, the touching points, to actually make the curve, entire curve. So using that logic, what we do is, suppose I draw a tangent here. The coordinate here is x0 comma f of x0. Okay. So what will the slope of the tangent here? The slope of the tangent will be f dashed of x0, right? So the equation of this tangent would simply be uh, f of x is equal to f dashed of x0 into x minus x0 plus, suppose I am at x0, then this term becomes 0, and I know that the uh, left hand side should give me f of x0. So that's why this is my equation of the line. And the idea here is of Legendre transform is that now you will represent the same curve which you were representing by this abscissa and ordinate, by this x and y coordinate. You will be representing the same thing using slope and intercept. By the way, this is not the y-intercept, sorry. Basically the slope and the intercept of the tangents. So this is the slope, but what is the intercept? What is the y-intercept of the tangent? To get that, I have to put x equal to 0 here. X equal to 0. That will give me f of 0 is equal to f prime of minus x0. I should basically write f prime of 0 into minus x0 multiplied by minus x0 plus f of x0, right? So my y-intercept is basically this, f of x0 minus f prime, sorry, again, my bad, this is just x0 only, x0, x0 into x0, right? So this is my intercept. The Legendre transform simply is that now I will be representing the entire curve as f prime of x0 comma f of x0 minus f prime x0 into x0. So this is my x coordinate, this is my y coordinate now. This is how, it's not exactly x and y coordinate obviously, but this is how I'm representing the curve. This is what I'll be using to represent the curve. So transformation from this kind of coordinates to these kinds of coordinates is called Legendre transform. That is what we learned in the lectures. Is there any doubt in this? Anyone? Is there any doubt here? At least say yes, no, something. Guys, at least respond. Say something. Say yes, say no, say something. Is it okay if it's not clear? I can explain again. It's clear? All right. So in that case, now the question that we are given is that what is the Legendre transform of the Lagrangian of a classical mechanical system? Lagrangian of a classical mechanical system has two components. Basically, it depends on q and q dot, where q is some coordinate, q dot is the time derivative of the coordinate. So it is basically a function of q and q dot. Um, Taking Legendre transform of q, just a moment. You can take Legendre transform of with respect to any variable, but here we are taking Legendre transform with respect to q dot particularly. So again, the same method. This is say my Lagrangian, this is my q dot, okay, and maybe this is some curve, okay. So this is q dot 0 comma L of q dot 0, right? So now I want to transform this to the intercept and slope intercept representation. How will I do that? L of say q dot in general is equal to, the slope will be dou L by dou q dot into q dot minus q dot 0 plus L of q dot 0, right? This is the equation of the tangent at this point. And now I want to know the y-intercept of this. What is the y-intercept? The y-intercept will be simply L of 0 is equal to dou L by dou q dot minus q0 dot plus L of q0 dot. That's the y-intercept. But we know that dou L by dou q dot, what is this? What is this? Sorry? I can't hear you clearly, bro. Dou L by dou q dot is the canonical momentum, right? Isn't it? Okay, anyway. So by Legendre transforming this, the intercept that I get is L of q0 dot minus, I'm calling this p, so p into q0 dot. What is this? This is a representation of the Hamiltonian, right? Basically negative of the Hamiltonian. This is minus of h. H is simply p q dot minus L. That's what we do, right? You sum over all the coordinates and whatever, and you get the Hamiltonian. So here taking the Legendre transform basically again changing from your normal x and y coordinates to another representation which has slope and intercept, and intercept is called the Legendre transform of the current of the previous variable. So the intercept that I get here, is the Legendre transform of the original function that I had. Basically here the original function was Lagrangian. So the Legendre transform of Lagrangian with respect to q dot variable is the intercept of this tangent. So the intercept of this tangent that I get is simply minus of Hamiltonian, minus of the classical Hamiltonian. So that's why option 4 is the correct answer. Okay. So this is your assignment. Basically, I'm taking the second question out. Again, it's very similar. It's the same thing practically. Yeah. So the question is, imagine a gas that has a fixed total internal energy and total volume where particles can flow in and out of the system. The Legendre transform of the entropy function versus the total number of particles may be expressed as. Okay, so now obviously entropy is a function of three variables, but we are keeping u and v both constant, and we are only allowing the change of particles. So simply again same thing, but now the x-axis is particles and y-axis is entropy, and you have to perform the Legendre transform. So all you have to do again is just at some point draw a tangent and find the y-intercept. The y-intercept is a Legendre transform of s with respect to this particular variable. Again the same procedure. S is simply dou s by dou n. That's the slope of the line at this point multiplied by n minus, suppose I call this point s of n star comma n star. Then this is n minus n star plus the y-intercept s of n star for now. Okay, and the y-intercept is simply this dou s by dou n of minus n star plus s of n star. What is dou s by dou n? We know that dou s by dou n is simply minus the chemical potential divided by temperature, right? Which is simply minus beta mu. Therefore, S of 0, which is the intercept, which is the Legendre transform also, is plus mu beta n plus S. This is n star plus S of n star. This is my Legendre transform with respect to the variable of n. This is the answer, S plus mu beta into n. Okay, since I'm not getting much response, I will assume that you are understanding what I'm doing. If at all you have doubts, please interrupt. Okay, so now next question. Okay, let me check if the recording is happening or not. Yes. Okay. Okay, so this one is a pretty straightforward question. You have U, which is energy per particle, given as 3 by 2 T plus T square by T0. That's what's given to you. And it's told that this is a quantum gas of non-relativistic particles in 3 dimensions. It's a quantum gas of non-relativistic particles and it is in 3 dimensions. So we know that for a non-relativistic gas in 3 dimensions, the relation between PV is basically 2 by 3 U, right? This relation is always satisfied. Okay, assuming that you know this as well. Um, so simply the whole task is to just substitute it here. This is P is equal to simply 2 by 3. Basically, here itself, I'm taking P is equal to 2 by 3 small u because u by v is small uv. That's what we're calling. So P is equal to 2 by 3 into the whole this function 3 by 2 t. What do we want? We want, acha, okay. So capital U has all of that multiplied. Oh, my bad, my bad, my bad. Here, this is not uv, of course. Sorry. This is simply capital U by n, right? Capital U by n is equal to this. So therefore, capital U is equal to 3 by 2 nt plus n t square by t0. And I said that PV is equal to 2 by 3 U, right? Capital U. Therefore, PV is equal to 2 by 3 of 3 by 2 nt plus nt square by t0 is simply mm, nt plus 2 by 3 nt square by t0 divided by volume, and you get the answer. The answer is just this option. P is equal to n by Vt plus 2 by 3 n t square by Vt0. A very straight, again, a very straightforward question. Okay, so there is one option at the bottom. Okay, so what they're asking is find the expression for the entropy of the ideal Fermi gas at low temperatures to leading order in the temperature. Uh, this is actually very uncomfortable for me, guys. There needs to be some response, as in whether you're getting it. Like, do you have doubts in these kinds of questions? No, so do you have doubts in these kinds of questions? Like, were you able to solve these kinds of questions, or there was some confusion? Because I would be able to address it better. It's like just one-sided. I'm just going on solving things. So some response would be more preferable. Were you able to solve these questions? By the way, assignment 3, tutorial 3, was it hard for you guys? Was it easy? What was it like? That's it was fine. You could solve all questions, or is there any particular question you could not solve? SG Mitran, like I don't know. Mitran, please, you also need to respond, and you too, Moses. Could you solve all the questions, or were there any particular question that you could not solve? It's a very simple, straightforward question. Sorry? Uh-huh. Able to solve all the questions? Okay. Fine. Nonetheless, it's, I suppose, my job. So I'll anyway go ahead. Uh, but had it been like, say, so my idea of asking was that if at all, particularly in these kinds of questions, you wouldn't, I suppose even this is straightforward because most of the expressions have been derived. But then if you would have, say, problems with derivations or something, I could have tried some of them here to show you, like, if you cannot derive those expressions, maybe you use those expressions and got the solution of assignment problems. But there is a possibility that the expressions derived in the lecture might be difficult for you, or applying them might be difficult. But fine, I suppose things were clear. Okay, so this is the question. You're supposed to find expression for the entropy of the ideal Fermi gas at low temperatures to leading order in the temperature. So at low temperature it means basically beta is much greater than 1, and this is your Q is going to be plus 1. So this is your Fermi gas, right? Okay, so I'll also have to refer to the expressions. For entropy, what do you need? You need um, PV and you need U, right? So okay, we want low temperature means beta much greater than 1. So it's just about large Z expansion, right? So in large Z expansion, we want to use the expressions of, let this get over. We want to use these expressions, right? We want to use the expression of U of PV. Yes, we need the expression of U to calculate entropy. What is entropy? Entropy is some basically function of U. You have U by T, right? Beta into U plus PV by T. So I also need PV. And you have uh, minus mu, n into mu, I guess, n into mu by T. This is what you have. So what I need is a expression for PV, expression for U, and I also need something to give me mu from here, mu by T basically, beta mu. So okay, I'll first use this expression at least. Okay, so as I said, S is equal to U by T plus PV by T minus um, N mu by T. So by the way, here leading order contribution to the entropy at, okay, wait, sorry, no, this is the question. That was the fifth question. We are doing the fourth one. The expression for entropy of ideal gas at low temperatures to leading order in temperature. If you see it here, if you look at this expression of U and of PV, So in U also you have one part which is constant, which is independent of temperature. So basically at zero temperature this will be the contribution, and at some higher value of temperature you will have this contribution as well. uh, at zero temperature for PV also this will be the contribution, and this will be the contribution at higher temperature, say T not equal to 0. So and also if you see the expression of entropy, it's U by T plus PV by T plus N mu by T. So here if you're talking about leading order in temperature, this divided by T with these constants itself, you might get confused that why is this not giving you the leading order in temperature, right? So suppose I'm writing S is equal to U, I'm taking the expression from here, 3 by 5 mu F divided by T plus the leading order here, 2 by 5, okay, N also is here, N mu F divided by T. So why is this not the leading order in temperature? Why will you not call this contribution the leading order in temperature? So the idea is that this is basically these contributions, the contribution to U at T equal to 0, the contribution to PV at T equal to 0, uh, gives you some entropy at T equal to 0, some constant entropy. But by third law of thermodynamics, you generally take that contribution to 0. You basically start counting your entropy from that level itself. So this expression where you're writing S is equal to this isn't exactly valid at T equal to 0. This expression can be written at some finite temperature, but at or near T equal to 0, this won't be valid. So, so what do you do at T equal to 0? Maybe I can use this expression. You might be familiar with this expression as well. Say TdS is equal to du plus PdV minus mu dN. This expression can be simply used. Okay, here temperature is on the left hand side, and this is in terms of the derivatives. Now we know that even in high temperature and low temperature expansions, we don't change the volume and the number, particle number. Even though we can change, as in sir has already mentioned multiple times, that the uh, mechanism can incorporate change in particle number and change in volume as well. But generally for expansions, for the expressions that we have derived, we have considered no change in particle number and no change in volume, so that the density remains constant, right? So since I am calculating entropy also, I can see that dV and dN I can take to 0. So ds is simply du, tds is simply du. And what is du? Du is equal to, I will use this expression, the first term goes away, the constant term goes away, and what do I get after that? 3 by 5 mu f into 5 pi square by 12 into 1 by mu f square into 2t dt. The only thing that's changing here is temperature. So I'm du is given with in terms of dt. So TdS is basically this. So what is ds? ds would be simply dividing this by t. So 3 by 5 mu f. Okay, 5 and 5 get cancelled. I can just simplify this better. This gets cancelled. This becomes 4 mu f pi square by 4 mu f square. So this also by the way goes into 2t divided by t. Here I divided by t as well because tds there was, so I divided by t as well into dt. So t also gets cancelled, and this is just simply integration over t. And here I had 2, this goes away. So what I am finally left with is pi square by 2, and here I have mu f in the denominator, and there is one t that comes up. Did I miss something? Oh, I missed n. Where did n come from here? Acha, there was a u by n here, right? So I missed an n, of course, because it is an extrinsic function, so it has to have n also. So this is the final expression or the answer that I get, which is here. Okay. What do you mean by the earlier expression of s? Uh, the full expression you're saying? So that we generally write. So this is basically my understanding that this entire expression s is equal to say u by t plus pv by t minus mu n by t. This expression is valid for say finite temperature or my point being that at zero temperature you will get some finite entropy. Okay, if you're using this expression at zero temperature also you end up with some finite entropy, but third law of thermodynamics basically tells you that that entropy you generally take it to zero and you start calculating your entropy from that level. So here if I'm uh, trying to include this as well, then at t tends to zero my entropy is shooting up. So basically this is what this tells me, that this expression of entropy in this form, basically not in the differential form but in the fully integrated form, I should not be using at zero temperature. So that's why I started with this expression, TdS is equal to du plus PdV plus mu dn. If at all you want to use that expression here, if you want to use this expression, PV has this entire thing and U also has this entire thing, you can. But what you will have to do is ignore the first term, the constant part of the total energy, because fermions at zero temperature also you do have some internal energy, you do have some pressure. So whatever is existing at zero temperature, if you ignore that part and then do this calculation, you will get the same result. But then you will have to include all the three. You will have to include mu into n, you have to include mu into n, you will have to include p into v plus u. All of these if you include, you will get the same exact answer. There is no difference. But this I found more conceptually correct, which is why I'm saying this. Okay. Hmm. So now what we want to do is at high temperatures. This is the fifth question. Again, for a gas of non-relativistic fermions in three dimensions, the leading contribution to the entropy at high temperature may be written as what? That's what we are being asked. Wait, was this the expression? No, it has mu f. Clearly not. We want T is very high. T is much greater than 1. So basically beta is much less than 1. Or basically Z is a small quantity. Z tends to 0. In that limit is what we want to solve this question. The only boring part is searching for these expressions. So we want small z expansion, not large z. Yes. So this will give me rho. Yes. So what I need is, okay. I don't need all of this, of course. Mm, I'll keep the final expression only. Yes, so these are the expressions that we require. So Z, basically Z is your fugacity, e raised to power beta mu is given in terms of density in this form. You have U, you have PV. All these expressions are already derived in the class. So I'm directly using those expressions. If at all you have problems with the derivation, you can come to me later, or maybe you can ask right now, whatever. Uh, but as far as this is concerned, I can directly use these expressions because they're given. So what do I want? Again, I want to calculate the leading contribution, the entropy at high temperature. So for the leading contribution, what will I do? I can simply take the first terms here and here. What do I want again? I want PV by T plus U by T plus N mu by T, right? So S is equal to PV. I can clearly see the first order contribution to PV is this only. So I'll put N here because PV by T is NT divided by T, which is N plus okay, fine. N plus here I have 3 by 2 N from the energy, from the internal energy. I'm taking 3 by 2 first leading order contribution. Plus now I want N mu by T. How will I get mu? All the entire game is to get mu. That's what's complicating the expression. There's nothing else. So mu I will be getting from this expression, right? Z is equal to rho C0 cube divided by pi raised to the power of 3 by 2, where C0 is equal to 2 beta h bar square pi square by m raised to half. So this is e raised to power beta mu. So taking log on both sides, what I get is beta into mu is equal to log of this expression, C0 cube divided by pi raised to power 3 by 2. And I can simply substitute C0 cube as well now. Why to delete 2 beta h bar square pi square by m. This is raised to the power of 3 by 2 because there is C0 cube and C0 has power 1 by 2. So that's why I have a 3 by 2 power here. Now this is just simple evaluation, nothing else. Oh, by the way, so here I can substitute something for beta as well because beta is temperature, and temperature also can be substituted in a much simpler form here. Obviously, we want entropy to be a function of U, V, and N only. So I could have used the expression, leading expression for temperature from here also. Sorry, not here, from the PV expression also. But that is not something that I will do. What I will do is I'll use the leading order expression here in the internal energy case because I will get temperature in terms of U and N, which are the extrinsic parameters which I want. So what is the value of beta here? This is U is equal to 3 by 2 beta N plus something. So beta is simply 2U, sorry, 3N by 2U. Okay, now substituting this, if I substitute 3N by 2 mu here through 2U, if I substitute that, this 2 goes away. What I get is beta mu is equal to 2 into, sorry, 3. 2 goes away. 3N h bar square pi square divided by UM. And that should be it. By the way, this pi also goes away. Instead of this pi, I can, yeah, this is what I can do. This is beta mu. And here also I have beta mu. This is just simply beta into mu. n beta mu. So the final expression that I get is S is equal to 3n by 2, sorry, 5n by 2, because here 3 by 2 plus n is 5n by 2 plus n ln of this expression, rho into raised to power 3 by 2, whatever. Let me write it down. I think there is some discrepancy in the option, maybe. Mu is to power 3 by 2. So simply what we are doing here is taking out v and writing everything as rho. So suppose I divide everywhere every expression by v here inside. So n by v becomes rho. So 5 rho by 2 plus rho into log of this, the whole multiplied by v. Now let's see what is the actual expression given. Acha, rho is simply substitute as n by v inside here. That's okay. We don't mind that. N by v, and you have 3n h bar square pi upon um. So there is only this discrepancy. You have a cube and a square here, but if you see clearly, a square is to power 3 by 2 is simply a cube, and this is also a cube. These both get cancelled out. So there might be some particular reason why they're writing it in this form. Maybe you can use some physical parameters and express this result. That's why they might be putting in a square specifically. But obviously, expression wise, it does not matter. It gets cancelled out. So this is the expression that you end up with. So 5 rho by 2 well expression, and you have 3 by 2 power. This one. This is your correct answer. Okay. Now that was this question. Here comes the next question. You have so next leading order contribution to entropy at high temperature. This is what we're supposed to find. So the first part of the expression we've already found out. Um, which one is it? It's 3, right? And you have only one option. So by process of elimination anyway, you can get the answer. But nonetheless, how do you calculate the next leading contribution? So it is fairly obvious. Here at least the contribution for PV is going to be this next order. You will include this expression. For U also, you will be including this expression. These are the next order expressions that I'm underlining. So for U, this is the next order part. For PV, this is the next order part. Just adding those will give you the answer. But now the question might be that why not include uh, mu as well, right? So mu also has some. Guys, am I audible? Someone can tell me. It's showing some network. Okay, okay. It was showing some network error on my side. Fine. So you might have the question that why not include mu as well, the contribution from mu, right? So that wouldn't be a wrong proposition at first, but the thing is, you had n outside when you are calculating entropy. So you have U by T plus whatever the other part is, PV by T plus mu into N by T. Okay. So here U is changing. We are going next order in U. We are going next order in PV. Both these are extrinsic variables. Here we are going next order in mu. So mu in the next order, you can see that the contribution in mu is coming inside of logarithm. This rho is being contributed by the n outside. Why am I particularly pointing this out? whatever variation or change will happen in mu, it will happen at the logarithm scale. And we are talking about the leading order contribution. These guys are contributing at rho square scale. If you can see here, this expression, I have one row here. I have one row here. So multiplying it by n, or what will we have? PV. So basically dividing by V, n by V, if we multiply, you will be getting one more row. So these are row square contributions. And what we'll be getting here inside this is going to be log something contribution. So that contribution is going to be much smaller now. If at all there is some change in mu, that contribution is going to be much smaller than these contributions that are coming from say PV or say total energy. So that is why we can ignore any kind of change or some other kind of contribution that comes in mu. All we can do is just think about contributions coming from these two guys. Now, why are we talking about rho here? Like, why are we talking about the leading order contributions in rho only? Because we are in what limit? We are in the beta much less than 1 limit. Basically, z is tending to 0 limit. That's the limit where we are in. So in this case, your mu has to be negative. Even for fermion, your mu has to be negative. And how does that go negative? Mu has to be either negative and very large, or mu has to be a little bit negative, and temperature has to be what? What does temperature have to be? Z is tending to 0. Temperature has to be large, right? So either mu has to be negative and very large, or mu has to be a little bit negative and very large temperature. These are the two possibilities that we have. For mu being negative in the fermionic system, it is generally required that you have very less density. The density of gas is very less. So that is why rho is the order which is telling you that say rho, linear order in rho is your first leading order contribution. Rho square is a second order contribution, which can be neglected say at very low densities. So that's why we are talking about rho specifically here. So the first order in rho contributions we've already taken into account. Now what we want to take into account is second order contributions in rho, which mu cannot give. Mu won't be able to give. That is why second order contribution in rho square, we are taking from only these two terms, U and PV. Okay, so we have the second order contribution here as 3 by 4. Okay, I'll write this down directly. I hope I've done this correctly. 8 root 2, this is 4. This is 2 root 2, right? Yeah, this is done perfectly. Okay, so I'm just picking this expression, putting it here. So this is the contribution from U by T basically. It's just U, it's not U by T. We'll have to divide it by T. And this is the contribution from PV side. The temperature is divided, everything is done. This is U. Okay. Uh, and I have to divide both of these by temperature, 1 by T. So what does this give me? This gives me S, right? And here in both of these I have N. So if I take out V common, these N's also become rows. This N becomes rho, and this row becomes rho square. This N becomes rho, and this row becomes rho square. Okay, so this is the entire term is same, pi raised to power 3 by 2 rho square h bar cube m raised to power 3 by 2 t halves, everything is same. It's just 3 by 4 plus 1 by 2. What does that give you? 5 by 4, right? So v into 5 pi raised to power 3 by 2 h bar cube rho square divided by 4 m raised to power 3 by 2 and t also raised to power 3 by 2. Why t raised to power 3 by 2? Because there is t outside. So this is my next order contribution, 5 by 4. I hope that's the answer. Okay, the question was bleaching. Fine. So this is the answer, right? 5 5 rho square pi raised to power 3 by 2 h bar cube divided by 4m and 1 by m. So m raised to power 3 by 2 basically, and t raised to power 3 by 2. Perfect. So this is our answer for the sixth question. Now, seventh one is nothing basically. Okay. Okay. The temperature at which the condensate fraction becomes 0.5 for a non-relativistic Bose gas in three dimensions. The condensate fraction becomes zero point 0.5. So we know the direct expression for condensate fraction is equal to 1 minus T by Tc raised to the power of 3 by 2. This gives me the condensate fraction, and we are told that this is zero point 0.5. Basically, this is half. So 1 minus T by Tc raised to the power 3 by 2. So T by Tc raised to the power 3 by 2 is half, and T is equal to, you just have to take half raised to the power 3 by 2. It gives you 0.6299 Tc, not 3 by 2. I have to take half raised to the power 2 by 3. Even if I take half raised to the power 2 by 3, this is the answer that I get, and this is the correct option. So I'm done with the assignment. If you have any more doubts in week 3, or you want some clarification, you can ask now. If you have some doubts in the assignment, you can ask now. Or let's meet for week 4 sometime, say on Friday or something. No doubts? It's okay. All right. All right then. So let's meet next time. Chalo, bye bye.